And so for this week's talk, I've chosen the title, Once Around the Fireworks Galaxy. And this is a marvelous picture of the Fireworks Galaxy on the left here. And I love this image because of the colors, because you've got that yellowy orange, almost brown tinge to the center, the nucleus of this lovely spiral galaxy. And then the spiral arms, which are a mixture of blue and red, pink colors, stretching out again with the brown streaks of dirty, dusty material going across them. So this is a galaxy that's once was considered to be part of the local group of galaxies that the Milky Way and Andromeda form, but we now know that it's about 20 million light years away, so it's probably really the member of the next little group further over, rather than being a part of our little group that consists of us, Andromeda, Triangulum, and a bunch of small dwarf galaxies. Again, I love this stunning image of it here. You can see a number of very interesting features. We're going to look at this one here, this rather strange bright blue region down at the bottom right on this image in a minute. But this is where it is if you want to go look for it. It's on the border between the northern tip of Cygnus and up there into the constellation of Cepheus, the King. So right on the boundary between the two. And as I say, 20 million light years from us. It's about 40,000 light years in diameter, and that's smaller than the Milky Way. We have a diameter about 100,000 light years, and so rather a small galaxy, and about half the number of stars in total compared to the Milky Way. But the surprising thing about it, and the thing that gives it its name of the Fireworks Galaxy, is that there have been 10 supernovae in the last 100 years detected in this galaxy. And compared to the Milky Way, which only produced one, that's quite amazing when you consider that there's only half the number of stars. So the rate of supernova explosions is 20 times. And we call it a starburst galaxy for that reason. And it gets its individual name of the Fireworks Galaxy because it's one of the most spectacular from the point of view of new supernovae. And it seems to have been doing this for a while, because if we bring on an image overlain with data from the Chandra Xray satellite, then we see the green and blue regions of X-ray emissions. There's a couple of very bright blue regions up here, greenish coloured one of a different energy here, here, there, and over here some more tinges of green. So these are old supernova shock waves that have expanded outwards and are still glowing and giving off X-rays. Probably contain quite a lot of radioactive elements that are still in the active stage of decay. Now, a couple of rather strange features that you can find in the Fireworks Galaxy. The first one is this one called the red ellipse, up at the northern side of one of the spiral arms here. This is a small version of the image here showing the red ellipse, and then we've zoomed right in. So on the limit, it's a little bit blurry and over amplified in this image, but you get the idea. And what we think is going on here is a very large open cluster of massive stars has been forming, and some of those massive stars have been exploding as supernovae, and the shock waves are responsible for those red rings that we see. So there's probably at least 3 different rings, maybe 4, that you can see in that image from multiple different supernovae in this very young and active star cluster with lots of very big powerful stars in it. Now that strange blue ring that I pointed out in the first image is called Hodges complex, And this is a beginnings of a bit of a clue as to what's going on. Here is Hodges complex in normal visible light, and then we've got a couple of zoomed in false color images showing the structure deep within it, with these, again, with these rings and loops of material. And so this was again once thought to be another of these giant star clusters forming many, many massive stars that were living their short but violent lives and exploding as supernovae and pushing all the gas into those ring formations and glowing so brightly and blue because of the surviving hot blue young stars. But a further possibility is that actually it's the nucleus of a recently swallowed and cannibalized dwarf galaxy that has collided with the Fireworks Galaxy and is mostly been eaten, but the tightly packed stars around the nucleus are still visible as Hodges complex. And that might be a clue as to why all of this activity is going on. It might be something to do with this recent merger with a smaller neighboring galaxy. Now, if we look at some of these supernovae, we're not going to go through all of them, but here's the list of the 10 supernovae from the Fireworks Galaxy in the last 100 years. They all get names SN for supernova, and then the year followed by a letter or a sequence of letters. And you can see we had 1917A, 1939C, and so on, single letters. Once we get up to 2020, we're now discovering so many supernovae in a year as a result of a lot of supernova surveys that they've gone past Z, round the alphabet again in lowercase letters, and then done that 26 times, and then 26 more times, and got to lowercase HH. So a terrific number. And so you can see that supernova 2004 ET here, and one of the most recent, 2017, needed 3 letters to catalogue it. So we're discovering so many more these days. But that's not why the Fireworks Galaxy has got so many in it. It just naturally is very, very active. It's not an artifact of discovery. So just have a look at a couple of the examples that we know about. So 2004 ET blew up on 27th of September 2004 and got up to a magnitude of 15.2, which is way too faint to be seen with the naked eye or anything, but observable with an amateur telescope. And by looking back at images of the galaxy prior to that date, they were able to track down the progenitor star that led up to the supernova. And it turned out to be a 15 solar mass red supergiant. So obviously the star had been through its evolutionary process, used all its hydrogen in the core, swelled up into a giant, gone through further stages, and eventually reached the point where it could no longer continue nuclear fusion because it was now trying to build the heavier elements up to and including iron in the core, and that causes the typical core collapse and supernova explosion that we're all familiar with. But in this particular case, it had a companion star, and the companion was a blue supergiant just prior to the supernova explosion. And that's quite interesting because it means the scenario is a bit like the graphic on the left-hand side here. In the early stages of the life of these pair of stars, they would have been a larger star that was a blue main sequence giant star and a fairly modest star of main sequence round about the same mass as the sun, maybe even a little bit less to begin with. But once the more massive star went through its evolutionary cycle very quickly, as massive stars do, and reached the red supergiant stage, it started to lose mass because the outer layers have swelled up so much that they cross over into the gravitational region controlled by the nearby partner star. They cross the Lagrange point here and go from one Roche lobe, as it's called, which is the region of influence where this star is dominant, into the Roche lobe of the companion. And that feeds the smaller star. And so it would evolve and grow into a higher temperature, more massive star, so from orange up to yellow or even up to white. And then gradually, as more and more mass is lost by the outer layers of the giant star, that's losing mass, and the mass transfer eventually slows down. But it usually, in this case, has fed the other star up to being a blue giant in its own right, in a fairly youthful condition, because it's being fed lots of extra hydrogen. Then, of course, the next step was for the red star to run out of fuel and blow up. And being so close together, that may partially disrupt the blue star, but their stars are pretty tough, and so the shockwave may have stripped some material off it again, and it may well still be there. So an interesting example, but it started with one of these 15 solar mass monster stars. And the most recent one, 2017 EAW, was a little brighter, magnitude 12.8, when it exploded in May of 2017. But again, we were able to track back using photographs and find the parent star. And this was also a 15 solar mass red supergiant. And that's not a coincidence. That's because the lifetime of a star depends on its mass. And there was an event that triggered off a lot of star formation, and it was triggered off a period of time ago that corresponds to the age of a 15 solar mass star reaching its supernova point. So that might be around about something like 10 to 15 million years. And most of these stars were formed at about the same time, caused perhaps by the merger with that small dwarf galaxy, triggering off a burst of star formation. And so what we're seeing is that the time is now up for all the stars that were born then that have 15 solar masses. The more massive ones will have blown up sometime a little earlier, and as time goes on, it'll work its way down the mass range, showing a surge in slightly smaller supernovae. So very interesting to be able to figure out the date, because all of these supernovae that are going off in the last 100 years are roughly these 15 solar mass red supergiants, because they're all in sync in their life cycle. Now, if we look at other galaxies that are also classified as starbursts, this is one of the favorite ones that we have for our Wednesday night observing sessions, very well placed at the moment, nice and high up in Ursa Major, Messier's object number 82, the Cigar Galaxy. And in a small telescope, you see a long, thin streak of light with maybe a strange tear or blot across the center. But in this Hubble Space Telescope image here, which can see a little bit into the infrared, we can see the main part of the galaxy looking very blue with some dirty dust lanes along it. And we're looking at a spiral galaxy side on here. The nucleus is a little bit obscured by the spiral arms, but does give a slightly yellow tinge through having mostly older stars. And the spiral arms are blue because they've got lots of young blue stars that were recently formed. And then you've got all this amazing structure where material is spewing out from the center. And that is probably where the black hole in the center, the supermassive black hole, has been feeding on infalling material. And black holes are very messy eaters. They spew a lot of it out along their magnetic spin axis, which may well not be aligned to the rotation axis of the galaxy, and so it gives you a cone shape of ejecta above and below the galaxy like this, forming these amazing tendrils and bubble structures. But the body of the galaxy is so blue, that means an awful lot of young stars were formed, and again at about 10 times the normal rate. And if it carries on like that, it's going to use up all of the spare gas, and then the star formation will come to a halt. It's about 12 million light years from us, and here's a composite image showing that ejecta and gas goes even further out away from the nucleus there. That's been put together using millimeter wave astronomy from the ALMA, the Atacama Large Millimeter Array down there in the desert in Chile. It shows that cooler gas stretches much further out. And we know what caused it for the Cigar Galaxy because we can see the culprit. It's Bode's galaxy, Messier 81, which is very nearby in all, just not only on the sky, but in 3 dimensions. It's also about 12 million light years from us. And about 6 million years ago, the two of them had a very near miss in space, and the larger gravity of Bode's galaxy tore into the structure of the Cigar Galaxy, twisted the spiral arms and created enormous disturbance. And it's that activity that's led to all of the starburst that's been going on since in the Cigar Galaxy. So that's another clue that mergers and near collisions of galaxies are responsible. But if you want final proof, here's the antenna galaxies. Again, a lot of starburst activity going on here. And these have been caught mid-merger. And you can see the two bodies of the galaxies bumping into each other, and the vast amount of new pink star-forming clouds that have been created where the gas clouds belonging to the two galaxies have collided with each other. That increases the density, it pushes the material together, and that push is just enough to trigger off vast amounts of new star formation. We can bring in the composite image taken with ALMA, again showing the heating of an awful lot of the gas clouds in this interesting spiral arrangement around here, showing that the path taken as the two galaxies were orbiting around each other, and that's responsible again for all of this star forming in this loop around the upper galaxy. But if we pull back, we can see in a wider context here the two bodies of the main galaxies merging together, and the enormous long tidal tails of stars that have been ejected from these galaxies out across space. This is part of the dynamics of what happens when galaxies merge together. They throw off enormous tidal tails, all to do with the conservation of angular momentum as the galaxies start to spin faster around each other. So that's the antenna galaxies, and again the starburst nature of it is revealed to be the result of this merger. This is this IC10. It's the nearest starburst galaxy to the Milky Way, and in fact it is a member of the local group. It's just 2.2 million light years away from us, so the same distance as the Andromeda galaxy, but in a different direction in space. And we know the distance because we've detected the good old yellow supergiant Cepheid variables in there and been able to use the Cepheid power law to figure out the distance. It contains a lot of very, very powerful stars, Wolf-Rayet stars that would be classed as W class stars in the past. We now just call them Wolf-Rayet. The W was standing for Wolf-Rayet anyway, and they're hotter even than the O class stars that are the hottest of the normal main sequence stars. And these W class stars have a very different look to them. They have only helium in their spectrum, almost no hydrogen. And this is because they have developed such energetic fusion in their cores due to their high mass that the outer layers of hydrogen that would normally be burning as the surface layers of all lesser stars have been completely blown away into space, revealing the inner helium shell that would normally lie underneath a layer of hydrogen. So that's IC10, and that's coming our way, and it will eventually merge with the rest of the galaxies of our local group. It's approaching at 350 kilometers per second, which is twice as fast as the Andromeda Galaxy. So it's going to get here first as well. Now, this is the large binocular telescope in Arizona, well placed up a mountain, with two of the largest astronomical mirrors, 8.4. It's the world's biggest pair of binoculars. And it was part of a search of 27 such starburst galaxies that we know about, lasting 4 years, looking to catch supernovae in action. It's a good place to search in these starburst galaxies because you generally don't have to wait very long. And indeed, they caught a very interesting event, and this goes by the designation N6946 BH1, and the event occurred in the spring of 2009. Suddenly, from March onwards, the brightness of this particular object in the FireworksGalaxy, I would point out, NGC 6946 is the FireworksGalaxy, and this particular object brightened up to become as bright as 1,000,000 times the output of our sun, and then faded away again. By 6 years later, in 2015, it was no longer visible to optical telescopes, even the best ones in the world. You can see in the images at the top here, it brightening and then fading away again. The images are black and white. The top one is V band, which means blue, really, blue and ultraviolet light. And the R band is the long wavelength red and infrared light. So you can see the slight differences in the way that it brightened and faded in the two bands. Now, this is interesting because the key fact here is it became as bright as 1,000,000 suns. And that's a lot, but it's not as much as a typical supernova. We have two typical types of supernova that we always talk about. We have the type 1A supernova, which is where you have an exploding white dwarf, and the white dwarf feeds off its large neighbor. When the large neighbor swells up to be a red giant, as shown here, the white dwarf from the earlier binary companion feeds off it until it reaches the Chandrasekhar limit of 1.44 solar masses, at which point it just can't take any more mass and explodes in a runaway thermonuclear explosion that completely destroys the star. And these type 1A supernovae are the brightest type of supernova. They're 10 billion times the brightness of our sun at their peak output. So our event that was discovered in 2009 was only 1,000,000 suns, and these things are 10 billion. So that's 10,000 times more powerful. What about the type 2 supernovae? These are giant stars that run out of fuel, as we were talking about earlier in the classic supernovae of the 15 solar mass stars that are blowing up in the FireworksGalaxy about now. They reach the point where their core contains iron and they can't go any further and explode as a type 2 core collapse supernova. But these, surprisingly, are 10 times less bright than the type 1A detonation of a white dwarf. Even though it's a bigger star that's exploding, actually the explosion is very inefficient it throws a lot of material around, but it doesn't convert very much of the mass into energy, whereas the white dwarf completely vanishes and all of its mass is turned into energy. So it's 10 times as powerful. But even these less bright type 2s are still 1,000 times more powerful than the event that was observed by the Large Binocular Telescope. Only 1 million suns for that one, 1,000th as bright. So what's going on? Bit of a mystery. Well, here is a couple of images from the Hubble Space Telescope, and this is kind of before and after. So in 2007, 2 years before the detonation, there's a large star there encircled with the blue ring, so you can see it. And then in 2015, afterwards, you can barely see anything at all, just a faint red glow right in the center of the circle there. And so putting this evidence together, what we figured out is that the original star was in fact a real powerhouse, an O-type blue giant, 25 solar masses, so considerably larger than the other ones we were looking at. It would have been, when it was still burning, 100,000 times as bright as our sun, and burning through its fuel. Even though it's got 25 times more fuel, it's burning it 100,000 times faster. And so the lifetime of these things is under 10 million years. And this one exploded, and we saw it in 2009. It would have been right up in this top left-hand corner of the good old Hertzsprung-Russell diagram. So it's would have been born on the main sequence here as an O-type 25 solar mass main sequence star, and had a very short life. It might have nipped across over here to become a blue supergiant, or a yellow supergiant, or even a red hypergiant star, as we would call it, before blowing up. But it wouldn't have spent very long doing that, because its total life is very short. Unlike the sun here, which is going to cruise along much more economically for another 5,000 million years. It's only halfway through its fuel. And these guys down here, the little tiny stars, they're going to live essentially many, many times longer than the current age of the universe even. These ones here live maybe 100 billion years, and the little tiny red ones 1 trillion years or more. Now we've traced the fading star also with the Spitzer telescope in the infrared to see what we can see there, and we can see a glow there still detectable even in 2015. That's about 5,000 times as bright as the sun, so it's faded a lot from the million solar outputs when it blew up down to just 5,000, and is glowing faintly in the infrared. So if we take the light curves that we've got from those observations, and we haven't got very many, but we can sort of construct a light curve. In the visible light, it grew brighter, stayed around for a few years, and then faded, and then exploded with an enormous bang there, and then faded away. And the infrared gradually rose to a peak and then more slowly faded away. Now this 25 solar mass giant star would have gone through a number of cycles, burning hydrogen to helium, then helium to carbon, carbon to oxygen, then on to neon, and then to elements like magnesium and silicon, and then finally silicon burning to iron. And each of those stages releases some energy, but it's a law of diminishing returns. Most of the energy budget comes from the hydrogen stage burning to form helium. And the last stage, silicon burning to iron, we normally tell people only lasts a matter of 6 months to a year. And that's what's happening here in this case, that the lull to the left of the graph here was the star in a state where it was forming inert silicon in the middle of the core, and then it brightened when the amount of silicon in there reached a pressure and density to ignite the burning of silicon to give iron by in the last gasp of nuclear fusion. So it started burning the silicon, so it got brighter, and it lasted for about a year burning silicon before it then started having to dump the ash from that burning process, the iron, into the core. And again, the inert core started to build in size and mass, and so the overall efficiency and power output of the star declined again down to here, until it reached the point just 6 months later where the iron core couldn't support its own weight anymore, and it collapsed down, and that leads to the explosion. So you can see that cycling in the light curve. So what actually happened? What was this peak? Was it a proper supernova? Well, what we think happened with such a large star is that a black hole formed directly. Stars in the range sort of 0 to 10.5 solar masses don't undergo this core collapse. They don't manage to get to the iron forming stage, and they end up as white dwarfs. 10.5 solar masses to 18 solar masses, they do indeed form an iron core and blow up as a type 2 supernova and form a neutron star in the center. As the core collapses, the implosion crushes the material and makes all the protons and electrons join up as neutrons, and you get a ball of neutrons in the center, the new neutron star. And that is very, very rigid and solid and dense, and the rest of the infalling material tries to hit it, can't penetrate it at all, and bounces off, and the shock wave tears the rest of the star apart and scatters the remnants to the four winds in space. And so that's what a type 2 supernova looks like. But this star at 25 solar masses would have attempted to form a neutron star, but the neutron star would have been more than the allowed maximum mass for such an object, so-called Tolman-Oppenheimer-Volkov limit, at around 3 solar masses of neutron star. And that then cannot support its own weight. And what we think happens here is it collapsed on downwards straight away, forming a black hole inside the star. And the black hole then proceeds to eat the inner side of the star from the inside out. As the material, unsupported, falls in, the black hole just grows and grows and eats it. And so there is no shock wave, no detonation, and the star destroys itself, but not by exploding outwards in a very, very bright event indeed. And that's why it was only a 1 million solar mass event, solar brightness event, compared to the billions for a type 2 supernova. And so we're going to have to rewrite this slide a little bit. This is the normal picture we give of the evolution of stars. Under that 10.5 solar mass limit, they go through the main sequence, form a small red giant that puffs off its outer layers as a planetary nebula, and then it leaves behind the white dwarf. Over 10.5 solar masses, you get a larger star, you get a red supergiant, and then a supernova explosion, which, if it's 18 solar masses or less, gives you a neutron star. And we used to say over that, the supernova gave you a black hole. And sometimes if material fell back onto the neutron star, that would then undergo a conversion to a black hole via this other wiggly line. But I think really the diagram should go from the red supergiant directly to the black hole via a different sort of nova event that we don't really have a name for. And so we're going to have to rewrite the textbooks as a result of this particular discovery, catching such a rare and massive event in the act, being able to see it both before and after. And so that's why I think studying these starburst galaxies like the FireworksGalaxy is so important, because it's building our understanding of just how these life cycle of stars really does work. And we're finding new things all the time.